All right, so here we go with another exponential problem. We have a population of bacteria. It's doubling in size every 15 minutes. At 8 o'clock, there are 1,000, and let n be the number of bacterial cells t hours after 8 o'clock. So write down a model for n in terms of t. So we're going to have n equals. This b is the initial amount, so that's going to be 1,000. Times, and this is exponential growth. It's doubling in size. We're getting bigger. The base is going to be 2. Now, what's the exponent going to be? It's going to be t divided by something. And that something is related to how long it takes to double. So every 15 minutes, how much of an hour is that? Well, it's 0.25. So that is our k value, t divided by k. It's 0.25 because we're dealing with a quarter hour that it doubles. Every 15 minutes, every 1/4 of an hour, we are applying this growth factor. And then plus some amount. Now, in this example, we don't have a value for c. I can eliminate that. Our asymptote is the x-axis. If we think about what this graph would look like, at time equals 0, we're up here at 1,000. If we were to go back in time from there, our population, we should expect, is getting closer and closer to 0, because we probably started out with 2 bacteria cells, or 1 bacteria cell, and then it grew from there. So our graph is looking something like this, with an asymptote way back here that would be y equals 0. But now we can use this model to find these populations at these times. So for part 1, n equals 1,000 times 2, well, 815. How many hours is that after 8 o'clock? Well, it's 15 minutes, so it's 1/4 hour. And I don't know about you, but I don't really like having that divided by 0.25. There's a better way that we could write that. We could clean it up just a little bit so we don't have to deal with dividing by the fraction. We could say that this is really 1,000 times 2 to the 4t. So 4 times 0.25. This is sort of like our k value. This is our time. And we end up with 2,000. Oh, that's double from what we started. And that should make sense because it tells us that it doubles in size every 15 minutes. That's good news for us. For part 2, n equals 1,000 times 2 to the 4 times what? Well, 9:24. Kind of a weird time. It's an hour. It's 1 point something. 24 minutes, that's less than 30 minutes, but I need to know really exactly what that is. So I'm going to jump to my calculator, and let me grab a calculator page. I need to take that 24 minutes and divide by 60. So 2/5, that's 0.4. So in my time, it's 1.4 hours. 1.4 hours is the same as an hour and 24 minutes. And this is something that I can plug into my calculator and I can get that answer. So let's go back to the calculator. 1,000 times 2 to the 4 times 1.4. There's our new population, 48,502. Wow, that's a significant growth. 48,502 bacteria. So in that hour and 24 minutes, we've gone from 1,000 to 48,000. That, my friends, is exponentially growing at a very, very rapid rate. And that's what we're looking at with this exponential growth.